All right, hello, and May the 4th be with you. Oh, it's Star Wars Day. What a wonderful day to start a new and our final unit of the year. So we are done with Trig. There was a couple things that we didn't get to go into as much detail as I would have probably liked to. And there were a couple of things that we didn't get to do a graded problem set that I love. But other than that, we got through at least the basics of everything. So I think you should be all set for pre-calc or honors pre-calc or wherever you end up going next year. So the next topic, though, here to finish our last 2 weeks of the year off is sequences and then series. So hopefully you were able to take a look there at some examples. If you didn't already before the video on the agenda there, you might have noticed there were some examples of just finding patterns. And so a sequence, right, is just a pattern of numbers, right? So it says here that a sequence is a set of numbers in a specific order, meaning that there's some pattern to it, right? So there's two specific types of sequences, though, that we want to take a special look at. And you should have seen these back in algebra, but I know it's been a while. And those were arithmetic sequences. So obviously that word looks like arithmetic, but when we put the emphasis on a different syllable, then we get arithmetic. So the other way to say that is when we're talking about an arithmetic sequence. So that is a sequence that has a constant difference. Okay, so if there is a constant difference, then it is known as an arithmetic sequence. So that means that between each term in the sequence, you're either adding or subtracting the same thing every time. Okay? And then our other sequence is geometric. We don't get to change the pronunciation there. It's not like geometric or something like that. It's just geometric. And that is a sequence with a constant ratio between successive terms. So let's just take a look here at a couple of examples. Determine whether the following sequences are arithmetic, geometric, or neither. So if you look here at the first one, right, so what's happening each time, right, is I'm multiplying by 2, right? So 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2, 32. So since I have the same ratio every time, I'm multiplying by the same thing. So in other words, the ratio of 4 divided by 2 is 2, 8 divided by 4 is 2, 16 divided by 8 is 2. So since that ratio is the same every time, that is a geometric sequence. Okay. This next one, there is a pattern to it. This is a sequence. Some of you may recognize this as the famous Fibonacci sequence. And so the way this sequence works, right, is if you add up two terms, so 1 plus 1, you get the next term 2, right? If you add 1 plus 2, you get the next term 3. 2 plus 3 gives you the next term 5. So this is a sequence. It's just not one of these two special ones. So the main thing to keep in mind here is that, there's loads and loads of sequences and patterns in mathematics. We just want to right now look at two specific types, and those are geometric and arithmetic. And then next year in pre-calc, you'll start up more than likely. Usually we start with this topic of sequences, and we just continue though and look at some other types. Of course, next year it may look a little different, but we'll see. But that's usually the plan. So, and then our last one here. So if we look right from 8 to 3, we're subtracting 5. 3 minus 2, we're subtracting 5. Or 3 minus 5, negative 2. Negative 2 minus 5 would be negative 7. So that is indeed then an arithmetic sequence. So arithmetic and geometric are the two special type we're going to look at. There are other special types, but those are the only two we are going to focus on for the next couple of weeks here. But we are actually going to spend more time looking at series because, excuse me, the sequence stuff here should hopefully be reviewed from algebra. But we're going to spend a lot of time with what are called then the series, which are adding up the terms of a sequence. So we'll get more into that later this week. So another thing to keep in mind then is that when we talk about writing formulas for sequences, there are two types of sequences or formulas that we can write. Okay, so there are what are known as explicit formulas, and then there are what are known as recursive formulas. So we want to take a look at both of those. So what is the difference between explicit and recursive? So we'll see that here in just a minute. So if you look here, I went ahead actually and plotted this for you just because it would save me time in the video. But if we have an arithmetic sequence, right? And so if I look at this arithmetic sequence, each time I'm going down by 3. So that means that my difference is -3. And if I were to plot the terms of this sequence, right? So this is term 1, term 2, term 3, term 4, term 5. So down here on the x-axis is the term number, and then up here on the y-axis is the term value. And so you'll notice then at term 1, I'm at 11, and so on. So what you have here, if you look at it, is a linear pattern. Okay, so arithmetic sequences are linear. Okay, so they are just linear with a constant difference between each term, like the slope. I don't know why that blank is so ginormous to write the word slope. Yeah, so essentially that constant difference right there is like the slope of this line, okay? It's just that we're not connecting the dots, right? They are just dots because they are just terms in the sequence. So you don't want to connect the dots, right? You just leave them, okay, as dots. And in mathematics, that is known as a discrete graph, okay? So discrete means just dots, not connected, okay? So if we know it's a line, right, if we think about the equation of a line, we know that one equation for a line is y equals mx plus b, right? Where m is the slope and b is the y-intercept. Well, the thing we have to be careful of here is that notice we are starting with term 1, not term 0. So we don't actually have the y-intercept. Now we could go back and figure out what it is, but a lot of times instead what we do is we write our formula like this. Okay, so I'll tell you what all those things mean. So we use subscripts to denote the term number. So when we say a subscript n, we are saying the nth term of the sequence. Okay, so that just means the nth term. A sub 1 then, or as I like to call it, A1, steak sauce, is the first term. Right? And then D is the difference. Well, if you look here, and then N, I should say, is the term number. So actually, if you look, all the pieces of y equals mx plus b are actually in this equation. The difference is that b here being the y-intercept is like a1, right? The only difference is that it's the first term, whereas the b would be the zero term, if you will. And then if you look here, d is the difference, so that's like the slope, multiplied by x, where x here is n minus 1. Now the reason that it's n minus 1 is because if you think about if you're going from the first term to the second term, you've only applied the difference once, right? So if you're trying to get to the 10th term, you've only applied the difference 9 times, so that's why it's n minus 1, okay? So, how would we write the equation then? So of this specific example up here, all right? So the way we could do that is, go back to this. So that means that the nth term is the first term, 11, plus n minus 1 times the difference, which was -3. So a sub n is 11 minus 3n plus 3. So a sub n is 14 minus 3n. So there's a formula to find the nth term of this sequence. So that is the explicit formula. So explicit means that if I wanted the 10th term, then I could just plug 10 in for n, right? So a sub 10 would be 14 minus 3 times 10. So explicit will give me the term that I want. Okay, so this formula that I wrote down right here, this is for the explicit arithmetic sequence. Okay, recursive is where we use our curly bracket, and then whoops. Oh, there we go. All right, so what this is saying, so the way a recursive formula works is it says, okay, I need to tell the person what the first term in the sequence is. So it's saying, hey, term 1 is, and so in this case, term 1 would be 11. Right? So you would tell the reader what the first term is. So let me just write it back out again here. Right? So this specific example then would be A1 is 11. And then A sub n would be A subscript n minus 1 minus 3, where n is greater than or equal to 2. Okay, so let me just talk you through what this is saying. So this is, if you were to come across a recursive formula like this, the way a recursive works, you have to give a starting position. So you're saying the first term is 11. So you would, if you needed to generate this sequence, you would write down 11. And then the way this line reads is it's saying A subscript n. So if I wanted the second term, it would be A subscript 2 equals A subscript 2 minus 1 is 1 minus 3. So in other words, A2 is take the first term 11 and subtract 3, right? Which would then give us 8. And then if I wanted the third term, it's telling us, oh, well, to get the third term, you would take the second term and subtract 3. Well, the second term was 8, so 8 minus 3 is 5. So the thing about a recursive formula is that it's not very useful other than the fact that it shows you exactly what the pattern is, right? So it's saying you would take the previous term and you would subtract 3, right? That's what you're doing. So you would take to get the nth term, you would take the term before it and subtract 3. And the reason we write n is greater than or equal to 2 is just to tell the reader that, hey, you only start doing this starting at term 2, right? This up here is term 1. So the thing about a recursive formula is a lot of times recursive formulas can be easy to write and easy to figure out, even for things that are not arithmetic or geometric. But obviously, if you wanted the 100th term, a recursive is not going to be that great because that means you've got to sit there and generate the 99 terms before it. So using a computer is a great way to do recursive formulas because it can generate them quickly. But for us, they're not as useful. All right, so let's take a look here just at one more quick example. Given this sequence, write an explicit and recursive formula and then use the explicit to find the 30th term. All right, so I look at my pattern. I see, is it arithmetic or not? If it's not arithmetic, then I can't use this formula we just did, so I hope that it is. So sure enough, it appears that we are adding 4 each time. So it is indeed arithmetic. So I know then that the nth term is the first term plus n minus 1 times the difference. So the nth term would be the first term 13 plus n minus 1, and the difference here was 4. Now technically that's a formula, but a lot of times we will go ahead and distribute the 4, so we get 4n minus 4. So my nth term would then be 13, forgot forgot to actually subtract the 4 there. 9 plus 4n. So there is a formula for this, and that's the explicit. Right? And then if I wanted the recursive, I need my brackets. Ooh, that was not my best bracket. Let's try again. There we go. So the A1, the first term, was 13. And then to get the nth term, I take the term before it, n minus 1, and I add 4, where n is greater than or equal to 2. Right? So there's the recursive. Okay, so if I wanted to generate the 30th term, I certainly don't think I want to use the recursive. Because if I'm going to use the recursive, then that means that I've got to start at 13 and just keep adding 4 until I get to the 30th term. That seems silly. That's why we have explicit formulas. So if I want the 30th term, a subscript 30 would represent the 30th term, I just take 9 and add it to 4 times 30. So that would be 9 plus 120. So the 30th term is 129. Okay? All right, so let's also then take a quick look here at geometric. It shouldn't take as long because very similar ideas for the formulas and such. So when we plot these, so we look at this, right? It started at 12, then it went to 6. So you were multiplying by a half each time, right? So that makes it geometric, right? Because you're multiplying by the same ratio each time. Okay, and so when you plot these dots, again, notice it is discrete, okay, right, so, but this time it is exponential. So if you're multiplying by the same thing each time, right, that's going to be exponential. And so the constant ratio is like the base of the exponential, right? So if you think back to couple months ago, right, our generic equation for an exponential was y equals a times b to the x. So it follows that exact same pattern. For an explicit formula, we typically use a g now to represent a geometric sequence. So the nth term for the geometric is the first term g1. So that's like a, right, the original amount, times r to the n minus 1. So g1 is the first term, r is the ratio, and n is again the term number. So again, it's n minus 1 because if I wanted to get to the 5th term, I've only applied the ratio, I've only multiplied 4 times. So the exponent then is to the n minus 1. Okay? So for this problem then, if I wanted to write the equation of this one, right, it would be g subscript n equals the first term, which was 12, times the ratio of a half to the n minus 1. And that would be it. So there is my geometric explicit. Please, 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 please do not multiply 12 times a half. Your Aunt Sally would be very upset. Order of operations says that exponent goes first. So that's it. You're done. You don't multiply the 12 times a half. All right. But then for the recursive, so the recursive, we do again the bracket, and we say g1 equals. And then this time we say, well, the nth term would be the term before it. But instead of adding or subtracting, we just multiply by r. And again, we say n is greater than or equal to 2 for that part. So for this particular problem then, g1 is 12. Right? So you're telling the reader where to start. And then you're saying my nth term is the term before it times a half, where n is greater than or equal to 2. So again, writing the recursive formula is a piece of cake, right? You're literally just telling the person, hey, take the previous term and multiply by a half. And that's how you'll get the nth term, right? But unfortunately, you know, if you needed to get far in the sequence, that's a pain. So just last quick example here. I know the notes are long today. Write the explicit and recursive formula for this sequence. So we look to see what it is, right? So we're multiplying by 3 each time. So that means that it is geometric. So that means that the nth term would be the first term 4 times 3 to the n minus 1. So there's the explicit. And then to get the recursive, well, that's not my best bracket. There we go. So then our first term, so G1 would equal 4. And our nth term is the term before it times 3. And again, n is greater than or equal to 2. Okay. So, and again, you would not multiply over here the 4 times the 3 and make that a 12, right? Order of operations says that exponent is happening first. So let's take a look at one last example here. So this time it tells us that 2,916 is a term in the sequence. If it is a term, state which one. Determine whether it is, I should say, and then state which one. Okay, so this time it's not saying find term number 2,916. It is asking, is 2,916 a term? Well, one thing you could do is just start multiplying by 3 and see if you get to 1, right? But just to use our formula here, so this means that the 2,916 is the number over there that we're trying to get, right? And so we're trying to then solve for n, okay? So we need to solve this problem for n. So the first thing we want to do is get that 4 out of there because we cannot, again, multiply the 4 times 3. So 2,916 divided by 4 is 729. And so now the question is, okay, is 729 a power of 3? So it's been a while since we did our powers and such, right? But it is indeed, right? This is 3 to the 6th. Okay, so 3 to the 6th, we can rewrite it. And so that means now we could set those exponents equal. So 6 equals n minus 1. So n equals 7. So yes, it is a term in the sequence because n turned out to be 7. The other option you could have done here, right, is you could have used logs, right? So we could have said log base 3 of 729 equals n minus 1. And so log base 3 of 729 is 6. And so again, we get 7. And so one thing to keep in mind here is if you got a number that was not a whole number, then it is not a term in the sequence, right? N has to be a whole number. So if you had solved this and found out that n was 7.3, then that is what would tell you, oh no, wait, that's not in the sequence, okay? So it has to be a whole number. All right, I hope that helps. Enjoy your May the 4th. I have a new Star Wars Lego that I'm hoping to start today in celebration, and I will talk to you guys soon.